Hi class, it's Bill back with Java 2's hashing exploration that we're doing this week. In the first two videos we set up the concept of hashing. In the second video we looked a little bit at specific code to implement a hash set for integers, and now we're going to continue looking at how hash sets would work for objects, and we'll finish up by looking at a couple of extensions like what do you have to do a hash map. So let's jump in where we left off. So if you want to hash an object, let's think about that a minute. Remember that hashing works with integers. So how in the world are you going to hash an object? So what is it that we want? What's the general thing that we would like? So let's look at the sort of quote contract that we want to implement for objects, or that we would want implemented, and then we'll talk about what we can do about it in our specific code. The general idea here, if you have an object and you run it through and you ask for a hash code, now don't confuse hash code with hash function. A hash code means you have to yield an integer, right? We need to get an integer out so that we can pass it to the hash function. So here we're talking about how an object yields its hash code. So if you get a hash code for the same object more than once during the program's run, it better give you the same integer every single time. Does that make sense? Because otherwise this whole thing falls apart. You have to have the same integer generated, because then you can't find it if it's a different integer. So that's the first rule. Right? If you invoke a hash code, if you ask the same object at different times during the run of the program for what is its hash code, it better give you the same number. Now, of course, when you run the thing another time, if you dump this whole thing out of memory and you start a new session, of course that can be a different number. But during the run of this particular program, it better be the same. The other thing is, if two objects are considered equal in the system, and I'm making air quotes that you can't see, if two objects are considered equal, then we would want the hash code to produce the same integer result. So does that give you a little clue that equals is going to be a method that you're interested in here, and hash code is going to be another one that is going to be related, right? Closely related. So if you consider the objects to be equal, they should produce the same integer hash code. Now, we know that collisions are inevitable, so it is not required that if the two objects consider themselves unequal, that they generate different, distinct integer results. However, it is certainly desirable that they don't clump themselves up. So for instance, if you were simply using the ASCII code of the first letter of a word when you were trying to do hash codes for strings, that would be bad because they would generate too many collisions right off the bat. So the desire is that your hash codes help to sort of spread things out over the integer range. So, but it's not required that every single one will produce a distinct integer, otherwise the collision problem is sort of mostly solved. So let's look at a kind of a different way that you could do this. Now Java has its own interesting way, but let's look at some ways that we could think about this. For instance, with our point class, let's say that we're working on a point where you have an x and a y value. How can you hash that? Well, hashing x plus y would not be great, because that would potentially, create two results, or two different additions could do the same result, and therefore maybe that wouldn't spread things out very well. What you'd kind of like to do is separate out the pieces. You'd like to numerically move them apart. So one idea here is you could take some constant, multiply it by y, and then add in x. And if you think about it, if you look at how all the bits would be on this, all of y's bits, most of y's bits would be first, and then most of x bits would be separate, which kind of moves them out through the number line. And this number is an example of how you could sort of push that thing over. So separating out the pieces, this would be a completely valid way if we wanted to do point. Again, Java has its own thing, but that would be something that we could do. So if we have complex objects, what might we want to do? How could we work with objects and sort of make our own hash codes in a smart way? Well, one thing you have to think about is built-in types like string already have a hash code. So If your particular object has an ID that is unique, for instance, a student ID, a social security number, anything like that, you could simply leverage the string hashCode method, and that would be fine, right? Because they've already figured it out. If somebody else has already done the work, why would we do that? So, for instance, in our student class, we might come up with a way to just use that. So we'll look at that in a second. So the other thing is, if you're going to implement comparable, we know that if you're going to implement that interface, you probably also want to do equals, and if you're going to do equals, you probably should do hashCode. So this adds to the list of what, as a good citizen, we should probably think about for each of our objects. Write a comparable, write an equals, write a hashCode, write a toString. Right? All of these things are probably things a good citizen would do. Now, just for fun, let's look at how the string class hashes. How does it generate its hash codes? Because they try to do exactly what we talked about, which is sort of spread things around a little so they don't lump up too much. So this is how they do it. Literally, this is the formula that they use here, where in each position, right, in the string hello, in each position you have an ASCII value. What they do is they take that ASCII value and they multiply it by 31 raised to the length minus position power. Does that make sense to you? So this generates this big old number. The second one like this, the third, the fourth, the fifth. So if you look at this, while they still overlap a little, there's not room to have a long enough string to have no overlap. But still, you'll see that you have some bits over here that kind of stand by themselves, and then you have some over here that kind of come into the overall string. So this one has a little room to itself, and this one kind of has a little bit of room, and then this one moves over here, and this one moves over here, and this one's over here. So if you now added all of that together, you could get that hash code. So it seems big, but of course maxint is plenty bigger than this, right? Not a problem at all. So again, the idea here that string is using is try to spread things out a little bit. Try to not make two strings use all of the same bits. Does that make sense? So now let's go look at how we could do with our student class. So if we took our student class, how could we leverage what we already know? Well, we would override hashCode, right? Here's our override for compare to, here's our hashCode for ID, right? So our hashCode says, look, we have a unique ID. Right? Every student ID has to be unique. Therefore, I don't even need to compare all the data and worry about all of it. I can just say, hey, take the ID and have it hash code itself. This is a string. Strings know how to generate their own hash code. So why would I do anything more complex? So that is a perfectly good way. Now you might ask, what if we don't do this? Right? What if we don't provide any kind of hash code? Well, the way that Java is going to work, if you don't provide a hash code, it's going to use the memory address of the object. The memory address of the object. That's going to be the thing that is the hash code, and therefore every object, whether you would consider it quote equal or not, is going to have a different place, is going to have a different memory address, and therefore it's going to be a different hash code for each object. Works completely fine, and for a given run of the program, things are not going to move around, right? The object's going to be where it's going to be. So that's what Java will do. So Java will make it work, and you can certainly let that happen if that's what you want, but certainly you can control it if you simply take and override hash code. You can control what you want to do if you'd like to. So there you go. So with hash sets of objects, what do we do? Okay, so this just says what I just said. Now let's look quickly at what a hash set would look like for a generic. So how is this different than what we did before? Well, one thing is that we're going to take a generic, right? E for element, and this is an important piece. You're going to want to make sure that each element that's in the hash set can compare itself. Because you're going to use comparable, you're going to want to be able to know whether two things are equal. So comparable becomes kind of an interesting piece here. So making sure that whatever hash set is taking in as a type is already implementing comparable is a nice way to say, hey, let's just make sure everything will play nice with us. Otherwise, you'll see the generics. Of course, we're making a hash set that is of type E. Right? The hash entry nodes are going to be of type E, and so will then the array that we create. Now, we know that this creates unchecked warnings, and we want to make sure Xlint is going to understand that we know about this. So when we do this cast, of course, we have to say, hey, we're going to suppress this warning on this for this particular reason. So, but everything else should look pretty much the same. The only thing is that now we've got the generics in place. Everything else works pretty much the same. You're going to take an E here, right? Otherwise, everything looks the same here. Nothing different there. The hash function, right? We're going to take in E. We're going to ask for the hash code of whatever that is, right? We know that every object has the ability to generate a hash code because objects will be used if nothing else. So we can guarantee that we have a hash code available for all objects, so that's a nice thing that we can do. And then the rehashing, again, we have this sort of the need to use the generic and this funny cast. We have to suppress that. There's a clever way to write that on one line, but that's another problem for another day. And then the hash entries themselves are going to have the data portion is going to be a reference to an E object. So that's different, but that's it. So all of that should make perfect sense. Again, it builds on what we've learned all quarter long, and when you glance at this code and see it, you should be going, yep, 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 yep. All of that makes perfect sense given what we know. So that's how you can write a hash set. Very straightforward. What else can you do? Well, let's talk about hash maps because those are certainly interesting, and depending on time, I think one of our projects will certainly use one of these things, or the project that we may have to kill at the end of the quarter if it's a short quarter, at least was going to use one of these things. So what is a hash map? A hash map's job, it still has this sort of set property of not taking in dupes, but it also has a mapping property which says, you give me one thing, I'll give you another thing. You give me a person's name, and I will tell you that person's age, for instance. Or you give me the person's ID in a string format, I will tell you their name or something else. So a map, the reason that a map exists is to map from one thing to another, but we'd want that to be generic as well. So this is an interesting thing when we declare a hash map, when we would have a hash map class, we're going to have two generics. Now, you may have seen this again in one of our projects where we actually did something very similar to this. In our, we used a tree map, and the tree map used integer here always, but the idea was very similar to this. So a double generic here, we're going to map from whatever type this is to whatever type this is. But everything else, the nodes are going to be a little more complex, but that's it. Every node is going to have three parts instead of two. It's going to have a key, and it's going to have a value, and it's going to have a reference to the next one of its same kind of node. So a hash map is, again, very straightforward given what we understand. We understand the hashing part, we understand the node part, and having two generics is sort of interesting in this case, but it doesn't really make things any more complicated, just a tiny bit. And we know in this case, K for key and V for value are very typical when you're using this thing. The generic K and V tend to pop up a lot. Again, they're never magic, but they're kind of a common thing to use. So hash maps, not very hard to implement once you understand the basics of hashing. So that brings us to the end of our discussion of hashing. Fascinating topic, widely used topic, and turns out really not too hard given what we now know. Hopefully you're seeing as we discuss these data types toward the end of the quarter, things are falling into place a lot more easily because we understand so much more. We understand all the generic stuff and the linked list and the traversals and all of those good things. And so now when we see these new data types, we can consume them and our brain can really adapt them very, very easily because we've got all of this under our belt. That's the desire here, right? When you leave this course, I don't want you to be afraid of anything, right? I want you to be able to say, yep, data structures can be interesting, they can be more complicated, but I have the tools. So thanks again for watching this video series. This brings us to the end of hashing, but there are still more interesting things to cover. So hope to see you back for another video another time. Thanks.